mathematicians in the past were trying to develop calculus, they were concerned with two big problems. The first one was called the tangent line problem. That's how to find the slope of a tangent line, or how to find the slope using just one point. And they solved that using the derivative. Now we're going to talk about the second big problem in math, and that's area under a curve. Now we can find area of rectangles and squares and circles and triangles and all those types pretty well. In fact, we can find them out exactly. But if we have something shaped like what you see here, it'd be a lot trickier to find the area between the curve and the x-axis. We always use the x-axis as one of our boundaries, just so you know. So how do you find that area? Now there's lots of different ways we could approximate that area, and that's actually how we're going to start, is learning how to approximate the area. If this was on a grid, like a Cartesian plane where you had blocks, you could actually count the blocks. That'd be one way. You could kind of give a rough guess. You could also draw shapes you do know, like maybe make this a rectangle that goes like halfway through the highest and lowest point, or different things like that. But what a guy named Riemann came up with was the idea that we would split this interval up into subintervals. So we see we have one big interval here, and he said, okay, well, what if we split this into smaller intervals? We'll just say 4 of them. He said, what if we then made rectangles and added up the area of those rectangles to estimate the area under the curve. Now again, these are just estimations. They're not going to give us the exact answer. So that was the idea Riemann came up with, and that's what we're going to do. There's different kinds of Riemann sums, and this lesson is going to be on left and right Riemann sums. So let me show you how we are going to do this. First it says Riemann sums are used to approximate area under a curve. I do want to say a couple things about this. Eventually, if you keep watching my videos or if you're in my course, you will learn how to find area under a curve exactly. But there's a few reasons that you need to learn Riemann sums anyway, even though they only approximate. Reason number one is because it's on the AP test. Now that's the worst reason, honestly, but that is one reason. Reason number two, it gives you kind of an idea. The exact way is related to Riemann sums, and it has to do with a proof involving Riemann sums. So it helps you kind of see how the math was developed. But the third and most important reason is, in real life, a lot of times we're not going to have an equation, and the equation is required to do the exact way. In real life, we're often going to just have data points. And if all you have is data points, then the only thing you can do is Riemann sums. So it's very common when people are dealing with real data that they're trying to come up with, that Riemann sums are the only option, and approximating is the only option. So let's look at this, then we'll talk a little bit more about Riemann sums and area under a curve in general. So it says use left and right Riemann sums to approximate the area under y equals negative x squared plus 5 on the interval 0 to 2 using 5 subintervals. So here's the idea. I know what negative x squared plus 5 looks like because I prepared for this, but it's okay if you don't. I'll show you what I would recommend you draw on most of them. It's really not necessarily draw the whole graph, but I will for this one. We're going from 0 to 2, and we want to split it into 5 pieces, 5 subintervals. So our total distance is 2, 0 to 2, splitting it up into 5 pieces, meaning each piece will be 2/5. So I need to have them spaced out 2/5. So now I am cutting it off right here. I don't care about this part over here. I'm not worried about it, because I'm only looking at it from 0 to 2. So I have 1, 2, 3, 4, 5 subintervals. Okay, so as I look at that first subinterval, I have a left endpoint at 0 and a right endpoint at 2/5. So to do the left Riemann sum, I'm going to take my left endpoint at 0 and I'm going to follow that all the way up to my graph. And I'm going to create a rectangle that has that height and draw it. So the rectangle I just drew has a base that is 2/5 wide. This is left again. Has a base that is 2/5 wide. and I can find its height by using my equation. I know I'm finding the height at 0, so I just plug 0 into my equation right here, and I get 5. So the rectangle I just drew would have a area of 2/5 times 5. Now let's add that to the next rectangle. Well, now we're shifting over. So now my left endpoint is 2/5. I'm looking at my second subinterval right here. My left endpoint is 2/5. My right endpoint is 4/5. So I'd draw 2/5 all the way up, make a rectangle at that height, and draw it down. Sorry, my drawing's not perfect, but hopefully you get the picture. Now this one also has a base of 2/5, and I get the height by plugging in 2/5, because that's what I use for my height. So I plug 2/5 into negative x squared plus 5. And I believe you get 4.84, but I'm going to double check that really quick. Yes, 4.84 is correct. Alright, so that would be our height, 4.84. Again, I'm getting that number by plugging 2/5, my left endpoint, into my original equation up here. So I'm plugging these numbers in here to get my y value, because the y value is your height. So now I move on to the third subinterval, where I've now shifted to where my left endpoint, my left endpoint is 4/5 and my right endpoint is 6/5. So I use my left endpoint, because I'm using the left Riemann sum, draw that up, draw a rectangle at that height, and come down. So my base is again 2/5, and if I plug 4/5 into my equation, I get 4.36 as the height. Okay, just two more. Need to add another one right here at 4. Now our left and right endpoints are at 6/5 and 8/5. So I use the left endpoint, draw it up there at 6/5. And again, my width is 2/5, or my base is 2/5. My height is what I get when I plug 6/5 in, which would be 3.56. And then my last one also has a width of 2/5, and I need to use the height at 8/5. So if I plug 8/5 in the original, I get 2.44. Alright, so I need to add all those together and see what I get. Well, let me go ahead and tell you one way you can shorten this process a good bit. This won't always be true, but for these problems, we are doing equal subintervals, meaning the base is the same every single time. So instead of writing out 2/5 every single time, it's a whole lot easier to just write 2/5 out front and then put all your heights in the middle, or in the parentheses. You can see that cuts down on my writing a good bit. And when I plug all those in, let's see what I get. 2/5 times 5 plus 4.84 plus 4.36 plus 3.56 plus 2.44. We get 8.08. So my left Riemann sum is 8.08. Now if you look at that, it should be obvious to you that that is too big. And the reason is all these rectangles overshoot my actual curve. So they've got a lot of extra with them. But that's still a useful number. Even though we know it's not perfect, we know that our actual area cannot be any higher than 8.08. So now let's do the right Riemann sum with the same equation. So now as I look at this, I go back to my first subinterval, do my right Riemann sum. I know my base for all 5 rectangles is going to be 2/5, so I'm going to put that out front. And this time, when I look at subinterval number 1, instead of using my left endpoint, 0, I'm going to use my right endpoint, 2/5. So notice that created a shorter rectangle, because we know previously from the height at 2/5 is 4.84. And then I look at subinterval number 2. My right endpoint this time is 4/5. So I draw up at 4/5 and make a rectangle. And I know my height at 4/5 is 4.36. Again, I'm just plugging 4/5 back in my original equation, y equals negative x squared plus 5. So then my right endpoint for subinterval 3 is 6/5, and then 8/5, and 2. So this time I'm using 2. I didn't before. But my heights at those would be 4.36, 3.56, 2.44, and 1. So if you notice, most of these numbers are in common. My left endpoint uses my left Riemann sum uses the left endpoint, but not the right. My right Riemann sum uses the right endpoint, but not the left. So there's really just one number different when we're solving these. And when we plug this in, 2/5 times all this, we get 6.48 for our answer. Now again, this is not perfect. If you look at my picture, this is undershooting it by a good bit. So my right Riemann sum is too small in this case. My left Riemann sum is too big. So I know at least that the real answer has to be somewhere between 6.48 and 8.08. Now, a lot of people in my class ask me when we're at this point, well, can't we just take the average? Well, you can, and that's certainly one way to get a more accurate guess. But when they ask for the left and the right, they just want you to do the left and the right. We'll actually talk a little bit in the next video about why sometimes left and right is better than even the more accurate methods. But when they ask for left and right, they just want left and right. They're not necessarily the most accurate ways to do it, but they are useful ways nonetheless. One way you can get more accurate while still using just left or just right is to do more subintervals. So for example, we did 5 subintervals. If we split this into 10 subintervals, our answer would be a lot closer to the real thing. Or if we did 100 or 1,000 subintervals, our answer would be really close to the real thing. And with computers, we can do that really easily. And that's one thing you can do with a computer is program it to find this, even with 1,000,000 subintervals, which at that point you're just going to be ridiculously accurate, even if it's not exact. Alright, so let's do the same thing here. Find the left and right Riemann sums for y equals x squared on 0 to 2 with 4 subintervals. So for this one, I'm not going to draw the whole picture. I just want to show you what I would recommend you draw. And that's really just the number line. So we're going from 0 to 2, and we're splitting it in 4 pieces. So the total distance there is 2, and we're splitting it in 4 pieces, so each piece should be 1/2. So those would be my intervals. And that much I would recommend you write. Okay, so now as we're trying to find the left Riemann sum, I'll use green for left this time. The base or the width of each of my rectangles is always going to be 1/2. That's going to be true the whole time. So instead of writing 1/2 every single time, I'm just pulling it out front, and we'll go from there. So for my left Riemann sum, for subinterval number 1, I need to use 0. So I plug in 0 and get 0 squared. And then for subinterval 2, I use 1/2, so that's 1/2 squared. For subinterval 3, I use 1, so that's 1 squared. And then for subinterval 4, I use 3/2, so that's 3/2 squared. So let's multiply this, see what we get. 1/2 times 0 plus 1/4 plus 1 plus 9/4. We get 1.75 for our answer. So the left Riemann sum is 1.75. Now let's look at the right Riemann sum. It also is going to have rectangles with bases of 1/2. But this time, when we look at the first subinterval, we're going to use 1/2 because it's our right endpoint. And the reason I'm squaring this is because of this equation right here. We're doing y equals x squared, so I'm just trying to skip a step and go ahead and plug in my point into my equation. And then for the second subinterval, I use 1. For the third subinterval, I use 3/2. And for the fourth subinterval, I use 2. And when you plug all this in, you should get 3.75. So again, that gives you a range over which your real answer must happen. Okay, so I want to ask this question. What is going to determine if the left Riemann sum overestimates or underestimates? What about the right Riemann sum? Because if you look back at the 2 examples I just did, right here, the right-hand sum seemed to overestimate, whereas on the example before that, the right-hand sum underestimated. So they switched places. Well, look carefully at this graph, and then I'll draw the next graph and see if you can figure it out. This was a graph of y equals x squared, so had I drawn it, you would have seen this. It turns out that what determines whether or not left and right are overestimating or underestimating is whether we are increasing or decreasing. Whether we're increasing or decreasing. So x squared, for example, is increasing. And when you're increasing, right overestimates and left underestimates. So increasing or decreasing is the key. When you're increasing, left underestimates, right overestimates. And when you're decreasing, left overestimates and right underestimates. Now you can try to memorize this if you want, but I'll just tell you honestly, I don't have this memorized. I just know that increasing or decreasing is the difference, because then I can just draw myself a picture. So for example, if they give me a picture and say, is the left Riemann sum overestimating or underestimating? Well, let's just say my picture looks something like this. Well, that's clearly increasing. So if I just draw a quick picture, let's say the left Riemann sum would do something like this. I know just by drawing that little bit that left underestimates. So I can remember left underestimates when I'm increasing. So I wouldn't worry too much about trying to memorize those, except for the fact that left and right are determined by increasing or decreasing. Because after that, it's easy to just draw a picture and figure it out that way than to try to memorize it. At least that's how I feel about it. Alright, like I said, a lot of times in the real world you won't have an equation. All you'll have are data points. So let's look at this one and talk about it. So it says using 5 subintervals, find the left and right Riemann sums. So the first subinterval is from 0 to 2, and then 2 to 5, 5 to 7, 7 to 11, 11 to 15. So that's subinterval 1, 2, 3, 4, and 5. Notice though the width of each interval this time is not the same. 0 to 2 is a distance of 2, 2 to 5 is a distance of 3, and so on. So I'm not going to be able to just pull out my base out front like I did in the others. I'm going to have to do each one individually. So let's just do left first. For my left Riemann sum, my first one is going to have the width of 2, because that's the distance between 0 and 2. And I'm using my left sum, so I would use this right here, and I would use 7 as my height. Your y value is always your height. Think about it. Y is your vertical axis, so y is always your height. So that's my first subinterval. And then from 2 to 5, that's a distance of 3. I use my left endpoint, which would be 2, so that has a height of 3. Then from 5 to 7, that's a distance of 5. My left endpoint is the 5, so I use 10 as my height. Then 7 to 11 is a distance of 4. I use my left endpoint, which is 7, so I use the height of 12. 11 to 15 is also a height of 4. My left endpoint is 11, so I use 13 as my height. So I plug all these in. 2 times 7 plus 3 times 3 plus 2 times 10 plus 4 times 12 plus 4 times 13. And I get 143 as my answer. Okay, now let's go back through and do the right Riemann sum. Again, we can't just pull one thing out front because they're not the same. So, from 0 to 2, that's a distance of 2. It's a width of 2. I use my right endpoint, which is at 2, so I use a height of 3. Then from 2 to 5 is a distance of 3. My right endpoint is 5, so that's a height of 10. Then I have a distance of 2, and I use the 12. And a distance of 4, and I use the 13. And then a distance of 4 again, and I use the 20. Okay, so when you plug all this in, you get 2 times 3 plus 3 times 10 plus 2 times 12 plus 4 times 13 plus 4 times 20. You should get, if I did it right, 192. So make sure if these subintervals are not the same, if they don't have the same width, that you do each one individually.